Welcome to the lecture series on process integration. This is module 4, lecture 2, and the topic of the present lecture is problem table algorithm. This is first part of the lecture. The graphical manipulation of composite curves to generate minimum target is time consuming and clumsy. That we have seen. To find out the energy targets, we have gone through a graphical representation in which we have plotted the composite hot and composite cold curves, and then shifting the composite cold curves toward the composite hot curve up to maintain a delta T minimum of a certain value. We have calculated the hot utility requirement and cold utility requirements. However, if the number of hot streams are very high and cold streams are also high, then using such a graphical method is cumbersome. Further, this graphical method has to be operated by a computer, and thus a alternative procedure is suggested, which is based on simple arithmetic and involves no trial and error. This algorithm can be converted into computer algorithms and can be very well used by the computer. This procedure is known as problem table algorithm. To show you how to use problem table algorithm, we have taken a stream data as given in example 1. It has 2 cold streams and 2 hot streams. The supply and target temperature of the streams are given. The Cp value, which is heat capacity flow rate, is also given, and delta H values are calculated and filled up in this table. The delta T minimum considered for this stream table is 10 degree centigrade. Now, let us draw the data available in the stream table in a TH diagram. The red one shows the composite hot curve and the green one shows the composite cold curve, and the minimum distance between composite hot and composite cold is this, which represents delta T minimum. Now, let us take the upper part of this and draw it. Now, if I try to have a horizontal heat transfer from composite hot to composite cold, then delta T available for this transfer is 0, because I am drawing lines parallel to T, perpendicular to the T axis, and thus the temperature for this horizontal heat transfer, the temperature drop for this horizontal heat transfer is 0, and the temperature remains constant during this horizontal heat transfer. So, this type of heat transfer is not possible. Now, to make it possible, I have to do some arrangements or some alternative arrangements. Now, in this arrangement, what is being done, that the composite hot stream is vertically shifted downward by an amount T minimum by 2, and the cold composite curve is shifted upward by an amount T minimum by 2. Now, while doing so, as the curves are shifted vertically, the distance between extreme part of the hot composite and cold composite curves remain constant, and that is why the hot utility prediction, which is Q h minimum, and the cold utility prediction, which is Q c minimum, remains same, though the hot composite curve is shifted downwards by delta T minimum by 2, and cold composite curves is shifted upward by an amount delta T minimum by 2. Now, when we do this, the hot composite curve touches the cold composite curve at delta T minimum, and this point is nothing but the pinch point. Now, if we do so, and then the upper part of the pinch and try to do the horizontal heat transfer in this case, then horizontal heat transfer is permissible, because now the temperature difference is delta T m during the horizontal heat transfer, and hence horizontal heat transfer is permissible. Now, based on this logic, the problem table algorithm has been devised, and let us take an example and demonstrate this problem table algorithm. For this, we take an example where there are 2 cold streams, 2 hot streams, and delta T minimum is 10 degree centigrade. Now, first job is to convert the temperature levels into shifted temperature levels. For this purpose, we will add delta T minimum divided by 2 to the temperature of cold streams, and we will deduct delta T minimum by 2 to the temperatures of hot streams, and this is as if we are shifting the hot streams in the downward directions and raising the cold streams in the upward direction by an amount delta T minimum by 2, which we have already demonstrated in the earlier plot. Now, if we apply this to cold stream C 1, then the supply temperature of the cold stream C 1 is 20 degree centigrade. Now, delta T minimum is 10 degree centigrade. So, delta T minimum divided by 2 is 5, and then we add up this 5 to 20 degree centigrade, it becomes 25 degree centigrade. Similarly, the target temperature is 180. So, when we add 5 degree centigrade to 180, it becomes 185. So, the two actual temperature levels of the cold stream C 1, which was 20 and 25, is now converted into shifted temperature levels and given by 25 and 185. Now, we deduct delta T minimum by 2 from the temperature of hot streams. Now, for this purpose, we take H 1 as the hot stream, and the supply temperature is 250. We deduct delta T minimum by 2, which is 5 degree centigrade from it. So, it converts into 245 degree. So, the supply temperature of H 1 is now 245 degree, and similarly, if we compute the target temperature, which is 40, now that becomes 35. So, when we convert the actual temperature of H 1 to shifted temperature levels, they become 245 and 35. In the similar manner, all the temperature levels were converted into shifted temperature levels and given in the table shown in the bottom. So, that is 25, 185, 245, 35, 145, 235, 195 and 75. Now, these temperature levels are put in decreasing order, and if a temperature level is encountered twice, it will be considered only once. So, in this case, if we plot the temperature levels, so the highest temperature level is 245 and then the next highest is 235 and then the next highest is 195 and so on so forth up to 25 degree centigrade. So, we number these temperature intervals. 245 to 235 is 1, 235 to 195 is 2 and so on so forth. So, we have 7 temperature intervals in this case. Now, we draw the cold and hot streams in this temperature intervals. The cold stream C1 moves from temperature interval 25 to 185. We should understand that the temperatures which has been given for this temperature interval are all shifted temperatures. So, C1 moves from 25 to 185. Similarly, the C2, H1 moves now from 245 to 35. The C2 moves from 145 to 235 and H2 moves from 195 to 75. Now, to exhibit the problem table and algorithm, we have this table in which there is interval temperature and number, stream population, delta T interval and then summation of CPC minus summation of CPH and then delta H interval and then we have surplus or deficit. To fill up this table, we take the shifted temperatures and then we define the temperature interval numbers in as done in the earlier slide. Then we show the stream population in different temperature intervals and then we fill up the last 4 columns by doing calculations. So, we take up the first interval which starts at 245 and ends at 235. So, delta T interval is 245 minus 235 is equal to 10 degree and this 10 degree is transferred here at this position and then we compute delta CPC minus delta CPH. Now, here it needs some understanding. In this temperature level which is temperature level 1, only one stream is there, that is hot stream, which stream number is 2. So, there is no cold stream here. So, summation CPC is 0 because there is no cold stream available in this temperature interval, whereas there is one hot streams whose Cp value is 0.15 and that is why the summation Cph will be 0.15 and hence the total value is minus 0.15 and this will move to this position. Then when we multiply this temperature interval with this value, then we get the delta H interval which comes out to be minus 1.5. Now, this shows that as delta H interval is negative, which means more heat is available than required in this interval. So, this interval has a surplus heat. So, this moves to surplus, it becomes surplus, and this is clear from this interval. There is only one hot stream which is ready to give heat in this temperature interval. There is no cold stream to take this heat. So, this heat remains as it is, and this can be transferred to a lower temperature interval, and that is why this much amount of heat is surplus. Now, in the similar manner, if we see in the temperature interval, which is number 2, the temperature moves from 235 to 195 and the delta T is 40 and the CPC summation CPC minus CPH is 0.15 and the delta H interval is 6 and this is deficit. That means, in this temperature interval only the hot stream whose stream number is 2 is available, and as well as the cold stream whose stream number is 3, the cold stream whose stream number is 3 is available. So, whatever heat which is available with the hot stream is not enough to heat the cold stream, that is stream number 3, and hence there is a requirement of 6 kilowatt in this temperature interval, and that is why it is deficit. Similarly, in this temperature interval, that is number 3, 2 hot streams are available to give heat and one cold stream is available to take heat, and the heat available with hot streams in this temperature interval 3 is more than the heat required by the cold stream in this temperature interval, and that is why 1 kilowatt extra heat is available in this temperature interval, and that is why it is surplus. In this manner, we can compute the heat available or required in this temperature levels 1 to 7, and they are given here. So, in the first interval surplus heat is available, in the second interval it is deficit, in the third interval it is again surplus, fourth interval it is deficit, and fifth interval it is surplus, and sixth and seventh interval it is deficit. Now, as per the rule of thermodynamics, the surplus amount of heat available in a temperature interval which is at a higher temperature can go down, but this surplus can go up. It cannot go up, because heat can only transfer from a higher temperature to a lower temperature, not from a lower temperature to a higher temperature. Keeping this in mind, and taking out the value of delta H interval, we can create a cascade which starts from 245 degree centigrade, here 245 degree centigrade and ends at 25 degree centigrade. This is the line 25 degree centigrade. Now, we can fill up one by one into this. So, all these temperature intervals are here, and the first interval is this, second interval this, third interval this, fourth this, fifth, sixth, seventh. Now, whatever heat will come from top will be a hot utility, and whatever heat will cross this 25 degree centigrade temperature level will be a cold utility requirement. So, our job is to now find out that what will be the hot utility requirement and what will be the cold utility requirement for this purpose. Now, if I want to take out a heat which is H equal to minus 1.5, the minus sign shows a surplus amount. It can be taken to the next temperature interval, which is temperature interval number 2. This is permissible, because heat naturally will flow from a higher temperature to a lower temperature. But if we try to do the reverse is not possible. I cannot take this 6 megawatt which is available here to this. So, it is not permitted. Now, so suppose we are adding 0 megawatt from the top, that means hot utility requirement is 0 megawatt now. If we do so, then here this is 0 minus 1.5, which becomes 1.5 megawatt. So, at this temperature level 1.5 megawatt is passing to downward. Similarly, if I can calculate this values here, this is 1.5 minus 6.0. So, this becomes minus 4.5 megawatt, and then here this is minus 4.5 minus 1.0, it becomes 3.5 minus 3.5 megawatt here, and here this is minus 3.5 minus 4.0, it becomes to minus 7.5 here. And similarly, I can calculate the heat which will pass through different temperature levels. Now, here I find that the maximum negative value is minus 7.5 megawatt. Now, this I have done through a algebraic calculation, but the question is, what is the meaning of this in terms of composite curves? Can I translate this to a real composite curve and can find out a relationship between these two? If I do so, here we see that is the hot composite curve and cold composite curve, and at this end they match, meaning that the hot utility demand is 0. In this case also the hot utility pushed to the system is 0 megawatt, and these values shows that the cold composite curve is above the hot composite curve for a considerable duration of length. So, from here to here it is over the hot composite curve, and this distance, this horizontal distance is minus 7.5 megawatt. In the previous lectures, I have clearly told that if a feasible heat transfer to take place, the composite hot curve should be above the composite cold curve, so that heat transfer takes place from hot to cold. Now, in this situation, this is not possible for all part of the heat of the composite curve to give heat to all part of the cold composite curve. In fact, it shows as if heat is passed from cold composite curve to hot composite curve, and that is why it is an infeasible solution. Now, to make it feasible, this cold composite curve has to be shifted horizontally, so that it becomes below the cold composite curve. So, we shift it so that it touches the hot composite curve at pinch point, and as the temperatures are shifted temperatures at this pinch point, the delta T minimum is equal to the delta T minimum, it is not 0, because the hot composite curve has been shifted downwards by delta T minimum by 2 and the cold composite curve has been shifted upward by delta T minimum by 2. So, even if they join at a point, the actual temperature difference at that point is delta T minimum. So, even if these two composite curves which are shifted temperature versus delta H are touching at pinch point, there will be a heat transfer at this point. Now, it shows that when it transfers horizontally, a gap is generated between these two, and this gap is 7.5 megawatt of hot utility, and similarly it shows that it needs 10 megawatt of cold utility. Now, this situation, which is a feasible situation, has to translate it to this, and the question is what we should, in which way we should operate, that this which is a non feasible solution converts into a feasible solution, and the solution represents this state of the hot and cold composite curves. Now, let us see how to do this, and when we do this, then the cold utility requirement will be 10 megawatt and the hot utility requirement will be 7.5 megawatt. Now, we search here that what is the maximum negative quantity. The maximum negative quantity is minus 7.5 megawatt. So, if I pass 7.5 megawatt of heat from the highest temperature level, then it will be able to give heat to all the temperature levels below, and when it percolates down or cascades down to this point, the heat requirement of this will be 0. So, we pass now the maximum value from the top. So, we add 7.5 megawatt from the top level, that is the level of hot utility. It will be at a temperature of hot utility, which will be obviously be more than 245 degree centigrade, and if I have considered delta T minimum to be 10 degree centigrade, then the level will be 255 degree centigrade, and this will be also a shifted temperature. So, a shifted temperature of at least 255 degree centigrade, from that temperature level heat of 7.5 megawatt will be passed to this cascade. Now, if I do this, the 7.5 megawatt crosses 245 temperature level, and here it becomes 9 megawatt, and then this becomes 3 megawatt, this becomes 4.0 megawatt, and this becomes 0 megawatt. And so, once this is 0 megawatt, that means the temperature through the temperature level of 145 degree centigrade 0 megawatt crosses, and hence it is the pinch temperature. But this 145 degree centigrade is a shifted temperature, it is not the actual temperature. So, to find out pinch temperature, hot pinch temperature, we will add delta T minimum by 2 to this. So, it becomes 150 degree centigrade, and for the cold we will do the reverse, that means we will deduct delta T minimum by 2, which is 5 degree in this case, and so it becomes 140. So, 150 minus 140 is 10 degree centigrade. Basically, we are doing the reverse, when we are doing the shifted temperature, determining the shifted temperature, we are deducting delta T minimum by 2 from the hot, and when we are reverting it, we are adding delta T minimum by 2. Similarly, for the cold, when we are converting cold temperature into shifted temperature, we are adding delta T minimum by 2, but when we are converting it to real temperature, we are deducting delta T minimum by 2. So, the pinch temperature is 145 and this is a shifted temperature. Then if we calculate this, so we find that 10 kilowatt will pass through 225 degree centigrade, and hence the cold utility demand is 10 kilowatt, whereas the hot utility demand is 7.5 kilowatt in this case. So, it is a feasible case now, because in the no level this is negative. I would say that this is not kilowatt, basically this is megawatt and this is megawatt. So, this is the case, feasible case. Now, as for this, we say this part is above pinch, this is d h means delta h, above part is above pinch region and this part is below pinch region, and there is no heat transfer from this above pinch region to below pinch region, and this is the pinch temperature level in shifted temperature. That is why we say that pinch divides the problem into two parts, and both parts are in temperature in thermal balance. Here the heat available with the hot streams plus the hot utility is equal to the heat required by the cold streams. Similarly, here the heat available with the hot stream is equal to the heat required by the cold streams plus cold utility. Now, we take a second example, the example number 2. So, we convert these actual temperatures to shifted temperatures. We add two columns here in the right side and convert them to shifted temperatures. As delta T minimum is 10 degree centigrade here for this example. So, we add 5 degree to this, so it becomes 25. We add 5 degree to the cold stream, this becomes 140. We deduct 5 degree to 170, it becomes 165. We deduct 5 degree to 60, it becomes 55, and then it is a cold stream. So, we will add 80 with 5, 85, 140 with 5, 145. Similarly, this was transformed to shifted temperatures. So, these are the shifted temperatures which are put in order from highest to lowest, and these are the temperature intervals, interval number 1, 2, 3, 4, 5 and 6. So, the temperature intervals 1, 2, 3, 4, 5, and these are the temperature levels basically T 1, T 2, T 3, T 4, T 5, T 6. Now, we can draw the cold streams and hot streams here. So, this cold stream, which is number 3, has got a Cp value of 4.25 and this has a 2.25 Cp value, Cp value 2 and Cp value 3. Stream available in different temperature intervals. So, here only stream number 2 is available in this temperature interval. In this temperature interval, 2 hot streams and 1 cold stream is available. So, stream number 2, 3 and 4 is available. In this temperature interval, all the 4 streams are available. In this temperature interval, 3 streams are available, 2 hot and 1 cold, and in this temperature interval, 1 hot and 1 cold streams are available. So, the delta T temperature interval, the delta T is 20 for this case 5, this case 55, this case 30 and this case 30. So, summation CPC minus CPH is 0.3 here, because this is 0 minus this is here the CPC is 0 and CPH is 3. So, 0 minus 3 is 3 here, minus 3 here, and in this interval there are 2 hot streams available and 1 cold streams. So, this is 3 plus 2 5, 5 minus this is yes, this is 4.25, cold is 4.25 minus 2 plus 3 5. So, this becomes 0.75. Similarly, we have computed the delta CPC minus CPH values here. Then we have delta H values in this temperature interval, the delta is minus 60, this is minus 3.75 and this is 82.5, this is minus 82.5 and 7.5. So, this has been computed like this, delta T into summation CPC minus CPH. Now, here this is the minus sign shows it is surplus, this minus sign shows it is surplus, this positive sign shows is deficit, this negative sign shows it is surplus and this shows the deficit. So, these are the values delta T are values available in this temperature intervals. So, we pass on 0 value of heat from hot utility. So, in this temperature level it 60 crosses. Similarly, we can find out that what is the amount of heat which crosses from different temperature levels, and this goes to cold utility. Now, this is minus 18.5, the maximum value is minus 18.5. So, to make this feasible, this heat transfer feasible, we have to add 18.5 units of heat from the top. So, we add from the top 18.75 that crosses this temperature level 165. Basically, the temperature level of the hot utility will be at least 165 plus the minimum delta T minimum. That means, this if it is a hot stream, then it will be added to 5, then actual temperature will come, then we will add another 10 degree centigrade to find out the temperature level of the hot utility. So, if I add this, so at this point it becomes 0 obviously, because we have added 18.75. So, it is minus 18.75, this becomes 0, and so this temperature level which is 85 is now the pinch point. And to find out the hot pinch and cold pinch, we have to add delta T minimum by 2 to this 85 and deduct delta T minimum by 2 to this 85 to know the hot pinch temperature and the cold pinch temperature. So, this clearly shows that the hot utility demand is 18.75 and cold utility demand is 75. So, this is the minimum hot utility demand and this is the minimum cold utility demand. I have already told you that pinch during the energy targeting gives you minimum hot utility and minimum cold utility which is required. It never talks about the maximum hot utility or maximum cold utility. Maximum hot utility and maximum cold utility can be anything, but it gives you the minimum required hot utility as well as cold utility. And this is the pinch point. Obviously, it is showing a shifted pinch point and actual pinch point has to be computed. Thank you.